I'd just like to introduce Paul Barnard, who's our speaker today. Paul has over 20 years of experience in the HVAC industry. He recently joined IWTM, and he'll be speaking today on their behalf. But he has worked in this sector for a long time, and he has experience working with a whole range of products, condensing boilers, renewables such as solar thermal, heat pumps, packaged commercial plant rooms, and a lot of his focus has been on communal district heating market over the last 10 years. So I'd like to thank Paul for joining us today. Just to give you an idea of the format for our session, the presentation will run for about 45 minutes. We do also have a brief introduction, which is a pre-record, and Paul is going to play that. And after that, we'll get on with the webinar lecture session. And I'll hand over now to Paul, who's going to run the video. So thanks, Paul.
My name is McCartney, and I'm the Managing Director here at Ecopipe Ireland. We have partnered up with IWTM to deliver chemical-free water treatment for closed-loop heating and cooling systems. In Ecopipe, we have been distributing TME multi-layer press-fitting piping system for up on 15 years. And we have noticed, just as you have in steel systems or copper systems, that corrosion is taking place after a few years in certain systems. These systems have been properly designed, they've been properly installed. However, more and more we are noticing component failures and system downtime. System downtime has consequential losses. If you have an office complex or a hotel and leisure complex, then there will be costs when the system is not working. The tradition has been to add inhibitors, silencers, cleansers, leak sealers, descalers, in conjunction with magnetic filters. Each one introduced as the rate of corrosion increases. We at Ecopipe prefer to encourage a preventative method. And partnering with IWTM, we encourage the use of VDI 2035 as the basic standard for water treatment in closed-loop heating and cooling systems. We have Paul Barnard here, technical sales engineer with IWTM. He's going to deliver the CPD, and at the end, he's going to take questions. Thank you very much.
So thanks for having me. Just give you a run through and an overview of chemical-free water treatment for closed-loop systems. So as you probably all know, sort of water is the lifeblood of any hydronic system, and the quality of that water is critical to the operating efficiency and the life and sort of components of those networks. So I'm just going to give you an overview of chemical-free water treatment. And in that, we're going to have a quick look at what is corrosion, what causes it, the technology behind chemical-free water treatment, the standards that are driving the approach to chemical-free, how we select the products, installation and maintenance, sort of benefits and advantages, and just run through a couple of case studies with you so you can understand the types of projects that we've been involved with. So what is corrosion? Just in simple terms, it's a reaction of metal with its environment. And why does this occur? Because the driving force of metals to corrode is the natural consequence of their temporary existence in a process form. So a rock has been taken out of the ground, it's been manufactured, beaten, pressed, formed into something that it maybe doesn't want to be. And so what the metal is doing is just wants to go back to be in its happy place and go back to being a rock. And that essentially is a simple way of understanding corrosion. So this slide here is just an image. The images on the left are different metals. So the top is iron, copper and aluminium, and you can see them, that's them all rusting or corroding, if you like. And then the images on the right are the iron, copper and aluminium in their original format, and you can see the similarity of how it's trying to get back into its original state. So there are a number of different factors that affect corrosion in hydronic systems, and there's an extensive list here. I'll just highlight a few. So the number one causal element of corrosion within closed loop systems is dissolved oxygen. It's the single most important factor. Without oxygen, corrosion can't take place. The conductivity of the water is a pathway for that corrosion, for that sort of oxygen to provide the corrosion. And is another key factor. The pH of the water is to do with the acidity and the aggressiveness of the water. So the more acidic, the more the aggressive, the more the corrosion takes place. And there's lots of other factors: temperature, chlorides in the water that can affect pitting on stainless steel, the galvanic potential difference of some metals, there's flow velocity, that, you know, things that can be designed out of your networks, but, you know, lots of factors that are affecting corrosion. So what is chemical-free water treatment? Obviously, what we're doing is we are looking to control the causal elements of corrosion within the water to stricter standards. So we're effectively engineering the water into a non-corrosive state. And when we say non-corrosive, we understand that you can never actually stop corrosion completely, but you can slow it down as much as possible. And there's a genuine sort of appetite in the industry at the moment for sort of cultural change, for looking at options to move away from harmful chemicals, and for sort of preemptive treatments and to, you know, to save the environment. And the methodology that we're applying conforms with Europe's most stringent guidelines. And we'll talk about those standards in a minute, but these include the VDI 2035, which is the main driving standards behind the chemical-free approach. The Danish District Heating Association have adopted it. It's adopted as a European standard. The CIBSE CP1 Heat Networks Code of Practice has written that into their guides and their best practice design guide now. So we're seeing a take up in that, and you'll find that a lot of the manufacturers that we install have this written into their O&Ms anyway, because, you know, their products are sold widely across Europe. So why is it needed? I mean, chemical water treatment can be effective. It's the methodology that's predominantly used across the UK currently, but in practice, it's very easy to under or overdose a system with chemicals. When you drill down into the methodology, you're trying to dose a system between 1% and 2% with a various cocktail of chemicals. And although, you know, a building may be handed over, it may be in its sweet spot, if you like, when you first take over that building. In the real world, these things go out of balance very easily. In the real world, you've got leaks on systems, you've got drain downs, you've got remedial work. People don't always top up the system correctly. Once that's done with the chemicals, it's not always looked after and maintained properly. You know, it relies on some specialist knowledge in terms of dosing, and obviously, you know, you've got the handling of harmful waste as well. The impacts of underdosing and overdosing, I'm sure you've come across them in your life as engineers. So local corrosion, biocorrosion, the fouling and sort of furring up of pipe work. starting to affect the performance of the system. We know that even just 1 millimeter of debris within a network can start to affect the performance of that network between sort of 5 and 10% in terms of efficiencies. So any sort of debris is going to affect the optimization and performance of a network. And with energy costs as what they are, is everyone's trying to maximize the performance of that energy transfer. So when you're dealing with chemicals, when you start to see sort of elevated results of total dissolved solids and evidence of scale and component failure, the solution is to actually, when you go to the chemical companies, is that you need to add more chemicals to the system to try and combat the evidence of corrosion. And actually overdosing a system can be just as damaging to the process, in that the chemicals can give a hard shock to the system when you're doing chemical flushing, and this can cause the failure of elastomeric materials, so your diaphragms and your pump seals. That picture on the bottom left hand corner is the seals on a pump that have gone, and that's often caused by the chemicals, and that then is accelerating the corrosion process, because you're getting water egress and further oxygen ingress into the system. And actually adding chemicals increases the conductivity of the water, and that can be an accelerant to the corrosion rate. So it's easy to see how you can get caught in a cycle of underdosing and overdosing a system. So what's the alternative? So chemical-free water treatment, we have a two-phase solution that will go on a network. So with two different pieces of equipment that would sit in your plant room. So the first piece of equipment, picture illustrated on the top right-hand corner there, is the resin filtration device, or deionizing unit, as we call this. And this is to ensure any makeup water, any fill water that's coming into that system is passed through the deionizing unit, and that's there to remove salts, limes, minerals, chlorides, and exchange them in the resin, removing carbon dioxide, and this manages the pH level of the makeup water, and also delivers it with zero conductivity. And then the second piece of equipment that we would have sitting on the system would be the reaction tank in your bottom right hand corner there. And this utilises the 18th century science of electrochemistry with sacrificial magnesium anodes to clean and maintain and optimise the water quality in the system. So how does it work? So the deionizing unit, or the resin filtration device. So this would sit in your network, typically between your mains cold and your pressurization unit on your network. So any makeup water that's pulled into the system passes through this deionizing mixed resin bed. And if you were going to a new build to fill a system from scratch, you would use either the unit that would be in situ in the plant room, or you do use a mobile version of this unit to fill the system via the deionizing unit. So these units sort of hold this mixed resin bed, and so what happens is there's a cation and an anion exchange. So all the harmful salts, limes, chlorides, minerals are passed through this resin bed, and they're exchanged for hydrogen and hydroxyl ions, which basically gives you pure demineralized water with a controlled pH of 8.2 and zero conductivity. And on the outlet of this unit, you would have a meter which would be able to measure the conductivity of the treated water that's been put into your system, and would be able to give you an alarm to indicate when the resin had depleted. And this system requires no external power supply. That would just sit there between your mains cold and your pressurization unit. Now, the effectiveness of the resin within the unit is really determined by the hardness of the water in the area of the install. So it would always be, we would check the postcode to do a water hardness check on that area. So the effectiveness of the resin, so just to give you an example, sort of 50 litres of resin in London, for example, which is a hard water area, would give you approximately 5,000 litres of demineralised water. But if you use that 50 litres of resin in Halifax, you probably get about 20,000 litres of demin water, because it's a much softer water makeup in that area. So the second piece of kit that would sit in the plant room would be the reaction tank, and this would sit sort of side stream across a working pump, taking a small flow of water, a small system pass of water, and it'd be sized to see the full volume of water, of system volume of water, pass through the unit over a 24-hour period. And central to this unit is sacrificial magnesium anodes, and magnesium is the least noble of metal. So the magnesium will give itself up ahead of any of the other host metals within that network. So it will corrode ahead of everything else. And as that magnesium corrodes, what it's going to do is burn through any dissolved oxygen that is in the water and control it down to a very low level. So it controls that down to less than 0.1 milligrams per litre. So generally, any raw water has about 9 to 11 milligrams of dissolved oxygen within that. And the reaction of the magnesium burning through the dissolved oxygen as it corrodes is that you produce magnesium hydroxide, and that is a naturally occurring alkaline solution. So that starts to raise the pH and affect the makeup of the water, and that will saturate into liquid form. And as you change the makeup of that water by changing the pH, and any incoming demineralized water comes into the system, like we said earlier, things want to go back to its original state. Water wants to turn back to its original state once you start to change its pH and strip out those minerals. So if we're going into a retrofit on an existing system, by changing the makeup of the water, we start to agitate any existing corrosion and debris that might have already taken place. So the water starts to hunt out ions around the network, and over a period of time it will lift any corrosion and debris that's taken place into suspension, and then that will get carried around either back to any strainers that are caught in the system, or back round to our unit where it will be caught and can be blown down. So just to talk you through the insides of that unit, as the system water comes into the unit, you've got a cyclone effect that's created by the shape of the vessel. And what that does, that will disperse any micro bubbles of oxygen that are still in the water, and they'll be vented out through the automatic air vent at the top of the unit. Any particulate will be dispersed and pushed down to the bottom of the unit. You've got a couple of hard magnets in there as well to catch any magnetite. And then there's a blow down valve at the bottom of that unit. So periodically you can blow down that debris, and that starts to reduce, clean up the system and reduce the conductivity of the water. And there's a filtration basket within that unit as well, which will catch any particulate, and that's sort of sized at 40 microns to start with, but then you can start to filter that down right down to 1 micron if required. So this is just the simple O-level chemistry behind the sacrificial anodes. So as metal gives itself up, as it corrodes, it burns through the oxygen, it will burn through all the nasties in the water. And in the process of doing that, it gives away electrons. And so on the front of that unit, you have a little amp meter, which will show you the activity of the anode, hard that anode is working. So when we're installed onto an existing system that has water quality issues, the swim meter will be hard right on that anode as the magnesium starts to burn through all the nasties in that system. And the equation there on the right is just showing you magnesium plus H2O produces magnesium hydroxide, which is commonly known as milk of magnesia. So you may have taken that to settle an acidic stomach in the past. So just a few words about some of the standards driving chemical-free water treatment. So the VDI standard, the VDI 2035, VDI stands for, is the Association of German Engineers. I'm not going to try my German out on anybody today. So it's the German equivalent of SIBSE, effectively 150,000 engineers strong, and is there to sort of research and advance the industry, you know, without any commercial interest. And the VDI 2035 Part 1 standard is primary standard behind the push towards non-chemical water treatment. And the VDI 2035 Part 2 was released in 2009, is recognised as the most authoritative guideline in Europe for the prevention of corrosion damage in water-based systems. And this has been adopted as the European standard. So it's adopted into EN 12828. That's why you'll find that it's written into most of the a lot of the manufacturers' manuals into their O&Ms. It's just that we tend to ignore the standard and just follow the BG guides, the BISRIA guides, in terms of how we're going to look after corrosion and bacteria growth in closed loop systems. So the key highlights of the VDI standard is that if you control these three elements to strict levels, then effectively you can remove the need for adding chemicals into a system. So this is your sort of you know, like your fire triangle. Is your holy grail of water quality treatment. So controlling dissolved oxygen to less than 0.1 milligrams per litre, managing your pH between 8.2 and 10, and having a conductivity of less than 100 microsiemens. And all those three elements are all linked to each other in terms of how they interact. So often we find on existing systems, if we're addressing a retrofit and we're cleaning up an existing system, we often get the dissolved oxygen and pH under control quite quickly. But the conductivity we could be dealing with years and years of corrosion. It might take longer to get under control, but once you've got that dissolved oxygen under control, the conductivity becomes less critical, and you can break that down over a period of time. But you know, there are ways of accelerating that breakdown as well. So how do we deliver the VDI? So correct design, planning and commissioning, correct sealing of the system to prevent oxygen entry is very key in this. So when we're doing a cleanup on an existing system, we often get the contractors to check the expansion and pressurization units are set up correctly. We've seen on some projects, we've had sort of commercial buildings where we've seen spikes in the corrosion occurring sort of every weekend. And when it was investigated, we saw that the sort of network was shut down at the weekends as the system cooled down because the pressurization unit wasn't set up correctly. The sort of automatic air vents were starting to suck in oxygen into that network at the weekends at times of low pressure and low temperature, and that's obviously fresh oxygen ingress into a network, and that was sort of accelerating the corrosion process. So just important to be aware of that. Obviously testing, monitoring, maintaining as usual are very important. This chart is just to give you an illustration of the VDI standards compared to what's in the BISRIA guide and BG50. What you can see is that it's very easy to understand and interpret the levels that you're trying to achieve with VDI. It's clearly set out, you know, your pH, your dissolved oxygen, your conductivity, your hardness, they're all targeted. Whereas when you go to the BISRIA guide, you'll find that some of these levels are as recommended by the water treatment specialists. So you're very much in the hands of the chemical companies in terms of them sort of marking their own homework, if you like. So what are manufacturers saying about VDI? I sort of mentioned this earlier. Many of them have adopted it and written into their water quality requirements, and some of them into the compliance of their warranty conditions. There's a list there of a lot of the manufacturers. I'm sure you'll be familiar with Wiesmann, Valent, Buderus, etc. Names I'm sure you've come across. And we've seen manufacturers in the UK start to sort of invoke the VDI standard when their equipment has fallen over due to water quality issues, and investigations have shown that they're not at that standard just through the methodology of adding chemicals. Yes, there is a sort of sea change coming. In Europe, we sort of are a tier 1 supplier to some of these manufacturers in terms of they brand our product and sell it out, with their boilers and their heat pumps anyway, as they're much more familiar with the chemical-free approach. So just a bit about product selection. So selection of the mains water treatment unit, the deionizing unit, as I said before, is dependent on the water quality locally in that area and the anticipated makeup rates of that network. So if you've got a tight, hopefully a very tight system with not too many leaks, you really shouldn't be putting more than 5% fill rate, per year, which is quite high. So we manufacture those units in different size units. So there's a 4 litre, a 12.5, a 25, and a 50 litre, and that's the literage is determined is the amount of resin that they contain. The reaction tanks, again, are calculated on system volume or sort of estimated around kilowatt output. And this makes a sort of a fairly straightforward process for designers in terms of unit selection. The units are sort of elegantly scalable in terms of, we do something from a domestic level right up to sort of a 300,000 system volume. The units can be put in array across the network. So, if physically you haven't got room in the plant room, they can be dotted around a system. For example, we're installed on Oslo International Airport as part of their critical infrastructure, and I think, they've got multiple heating and chilled water networks around the site. So, we've got sort of 20 or so different units installed across that site in different locations. So product application, we're applicable to all types of commercial and residential building, all sizes of commercial and residential building. We're applicable to new build. We're applicable to retrofit onto an existing system where you're addressing water quality issues. And we're applicable, for the pre-commissioning, pre-con fill and clean process in the new build process. So just talking about the pre-con fill and clean. So if you're going into a new building, you've got a new heat network, for example, the process for us would be you would fill the system with bacteria-free demineralized water through sort of a mobile filling device. So we're engineering that water, we're controlling the pH and the conductivity of that water from day one. You would vent the system in the same way you would if you're doing a normal fill using chemicals, removing any pockets of air that are in the system. But here's the difference. We do not drain or partially drain at any time in this process. So it's a one fill process. So if you're normally filling with chemicals, you would fill and flush. And generally speaking, you probably fill and flush sort of and end up dumping 5 times system volume of that network plus chemicals to drain in the process of cleaning it and getting it into the correct state. So what we're doing is we will fill once, we then use the demin water as our cleaning agent. And as we talked about before, it's going to leach for ions. You can run that demin water at your BISRIA high velocity rates to do your builder's clean and catch any debris and swarf and stuff that's built up into that network. Your sort of pre-con fill and clean companies can catch that in full bore side stream filtration, without dumping the water, and then you can do what we call a resin polish. So you can divert that system water through one of a mobile deionizing unit just to make sure it's hitting those standards in terms of the pH and the conductivity. So you've got clean demineralized water from day one. In cleaning up existing system applications, there's no requirement for chemical flushing or dosing. There's no dumping of water. We're cleaning the water in situ. So whatever the state of that system water is to start with, you're going to be installing our unit within the plant room, our reaction tank and our deionizing unit. So we're a gradual, non-aggressive cleanup that's going on in the background. So we can start to scavenge the dissolved oxygen in that network, start to clean up the sludge and slurry. And this means there's no shock to the system. There's also no interruption to the operation of the building. There's no downtime. So if you've got, critical infrastructure and everything is critical these days in schools, care homes, hospitals, office buildings, people don't want any downtime. So this cleanup process can carry on in the background while everything else is working operationally. So just a couple of illustrations again. So the one on the left is the deionizing unit. So again, just to reiterate, installed between your mains cold and your pressurization unit. The little blue meter there is measuring the flow, the fill rate, and also will give you an indication on the conductivity of the water coming into the unit. So when the resin's expired and depleted, the conductivity will start to go up and indicate you would need to change the resin. The illustration on the right here on cleaning an existing system. So the top unit is the reaction tank, which should be on side stream filtration, and the bottom unit on wheels is a mobile deionizing unit. So what it's showing is we're diverting the existing water through a deionizing resin bed, and this would be to help accelerate a cleanup. So on a cleanup of an existing system, after 2 or 3 months of operation of the side stream unit, we might want to do a resin rinse on the network to help break the conductivity of the water. But it's not always necessary, it just depends on the state of the existing system. So just a few words about how we control bacteria with the chemical-free approach. So most of your bacteria are thriving in an environment of a pH 4 to 8, and we're always looking to push the pH 8.2 and above. So we're creating an environment that's hostile for them to exist. So your pseudomonas, they don't like the pH above 8. Your aerobic bacteria, as the name suggests, require oxygen. So we're scavenging that dissolved oxygen. We're starving them of their food in that environment. Your anaerobic can live without oxygen, but doesn't like the pH above 8. And then your sulfate reducing bacteria and your nitrate reducing bacteria, your SRBs and NRBs, again, they tend to live off the biofilms that's created by dosing with chemicals. So when you dose with chemicals, you're sort of creating this, this film around the pipework or within the pipework to prevent the water from reacting with the metals. And as those chemicals degrade, they become food for those SRBs and NRBs. So what we're doing is we're stripping all of that out and we're creating an environment that's hostile for the existence of and growth of bacteria. Protecting aluminium, as you're probably aware, sort of aluminium is much more susceptible to corrosion, and VDI states that ideally to control the pH at no more than 9 for aluminium alloys. You'll see in manufacturers' manuals they sort of state between 8.5 pH and 9. But VDI acknowledges that this is difficult to deliver in practice. But what it also acknowledges is that you can, if you go back to the triangle with the pH, the conductivity, and the dissolved oxygen, if you're controlling the dissolved oxygen down to very low levels, if you've got the conductivity under control, it doesn't matter if the pH drifts a little bit. And the second level of protection is that you've always got the magnesium anodes, which is your least noble of metal, as we said before, which is going to give itself up ahead of any aluminium in the network. So it's very effective at looking after systems where aluminium is present. So just installation wise, very easy to install. Generally, with the reaction tank would be installed where a dosing pot would be, so across the inlet and the outlet of a working pump in the plant room, sort of half a day to install the equipment. This is just showing you schematically. So you've got your outlet of your pump will go to the inlet of our reaction tank, and the outlet of our reaction tank will go back to the inlet of the pump. Now, if there isn't a connection in the plant room, you can put your own trickle pump onto the network with our system, but obviously that requires power, and if we can go across an existing pump, it means there's no power again required to our unit. The manifolds you can see on the outlet there's a bit of kit we supply with the reaction tank, so that's got a flow meter, so we can measure see how much flow we're getting through the unit. Regulating valves, so we can regulate the flow rate, so different sized reaction tanks will require different sort of flow rate, between 5 and 20 litres per minute. And then the 4-port valve, a Cyril valve there is to give us a connection to be able to connect onto a deionizing mobile unit if we should wish to sort of accelerate the cleanup process on one of the units. The 2 gauges there on the front of the unit are differential pressure gauges, so they'll give you an indication when the basket's full inside the unit and would need to be taken out and cleaned. And then there's a swing meter. You can't see it in this photo, but you'll see it in another one in a minute, which is showing you the activity of the anodes and will be an indicator of when the anodes have expired and need replacing. So the installation of the deionizing unit, the resin filtration beds, as I said before, this would just sit between your mains colds and your pressurization unit before your quick fill. So any makeup water that's coming into the unit is pushed through the deionizing unit. So we're controlling that makeup water to a specific pH and a low conductivity. So the maintenance process is very simple. You've got your 2 consumables on our units, your anodes and your resin. The anodes generally have a 3-year life on a clean system. If we're going onto a retrofit to clean up an existing system, we would always supply a spare set of anodes with the unit, because we expect the anodes to burn through within year 1 in terms of doing all the work up front in stripping out the chemicals and burning through the dissolved oxygen in the network. Blowing down the unit, similar to doing the blowdowns on a normal dirt separator. And then your water analysis is simplified, because any water sampling, we're only really testing to VDI standards. So we're testing for the evidence of corrosion. We're not having to test the water for levels of chemicals, for levels of molybdates, biocides, all those types of things. So a simplified sort of maintenance process that can be delivered by sort of in-house mechanical teams. So it's just like apprentice level engineering in terms of maintaining those units, changing the resin, changing the anodes. Very simple, a simple procedure to do. allows, as I said, to be brought in-house in terms of maintaining these bits of equipment, can sit in your normal ppms. This is the swing meter in the bottom right-hand corner that's indicating the activity of the anodes. So when the anodes have expired, you're in that service red on the left there. In normal operation, the anode, the dial should be in the middle, and when the anodes are working hard, the dial will be hard right. Again, easy to flush down. You've got no COSH or wastewater licenses required because we're not dumping any harmful chemicals or your chain of custody, all that sort of stuff that is normally required with the chemical approach. So the benefits and advantages, primarily it's the efficacy, how well it works. The units, you're not relying so much on this percentage dosing. You can undersize our units, but the jump between different sized units is quite considerable. So for example, we've got a unit that does up to 1,500 litre system volume, then it jumps to a 5,000 litre system volume, then that jumps to a 10,000 litre system volume, to a 25, etc., and going up. So you can undersize, but it would be careless to do so. And oversizing doesn't matter. It will just give you a cleaner, quicker system. The anodes, if you like, are self-regulating, so if the system is in its sweet spot, if it's under control, the anodes would be dormant. If there was a fresh ingress for oxygen, there was some remedial work done on the network or whatever, the anodes would reactivate themselves and start to do their work again. So simple from that point of view. So environmental concerns: reduce wastewater. We're breaking the cycle of dumping and retreating water. Reduction of plastic waste. You're not having to store, the containers for chemicals, and so forth. Operationally, improvement: clean, demineralized, oxygen-controlled water gives you the best form of heat transfer, and this is becoming more and more important as we're using sort of your renewable energies with heat pumps at lower temperatures, where you're trying to achieve, you've got COPs on heat pumps, and if you add anything into that network, even adding glycol, if you read the manufacturer's instructions, can affect the performance of a heat pumps by up to a quarter in terms of its efficiency. So, we would sort of advocate using clean demineralized water, remove the need for glycol. You can control antifreeze on your outside pipe work through other methodologies, through antifreeze valves, through trace heating and stuff like that. But keep the closed loop system with clean demineralized water will give you an optimization in terms of the performance, so improving system efficiency, extending the asset life, or delivering the best asset life for those pieces of equipment. Obviously reducing pipe blockages, reducing breakdowns, downtime. Just optimizing, the energy transfer on that network. The nice to haves is the sustainability angle. So we're avoiding the use of harmful chemicals. We're creating an environment that's safer for your engineers to work in. As we said, breaking the cycle of dumping and retreating water, reduction of plastic waste. The consumables for our units are delivered in cardboard boxes. We're not storing anything in plastic drums. You're avoiding the need for large volume deliveries of chemicals being transported through local community, and this is all ticking boxes in your environmental sustainable governance boxes. Cost, obviously, one of the important factors. So cost benefits, capex wise, like for like, typically a 2 to 5 year return on investment, maybe sooner if remedial works was needed. When compared to chemical flushing, we're generally cost positive, because that can be quite an expensive procedure, quite intrusive. From an OPEX point of view, so looking after the building going forward, sort of conservatively estimate we're about 10 to 20% cheaper from general chemical regimes. because you know, your maintenance can be delivered, can self-delivered in-house. You're not having to employ specialist water treatment companies. And then on the new build side, you know, chemicals removed from your pre-con, fill and clean. Sometimes, you know, that can be influential in terms of the dumping of water from sort of water neutrality point of view. We're seeing, you know, some developments being refused planning permission because of the impacts on the water consumption in the area and so forth. So, you know, these things can assist in terms of achieving planning. So just to finish, a few case studies, and then hopefully we've got some time for a couple of questions. So the first one, this was just a commercial building, commercial office building in Canary Wharf, where they had issues. They had 3 out of 4 of their 1 megawatt boilers failed within the first 2 months of operation. The warranty was invalidated by the manufacturer due to the VDI standards quality not being met. So when we got called onto site, the conductivity of the water was at 2,100 microsiemens. Boiler manufacturer's requirement was no more than 300 microsiemens. And on this site, this was the end of July, they had to get new boilers installed before the start of the heating season. So they were faced with quite high costs for chemical flushing. We were cost positive against their cost to actually buy and install our equipment. So they bought the reaction tank, the deionizing unit. We carried out some extensive resin rinsing, so diverting the system water through a mobile deionizing unit in order to meet the time deadlines they were working to get the conductivity of that water broken down within 30 days to meet a deadline so they could get the new boilers installed. So this graph here is just the results from a third-party corrosion monitor that we sometimes install onto these networks to demonstrate to the client the efficacy of the product. The bottom graph is the temperature of the network. The top graph is the corrosive state of the network. So the blue line is the corrosion monitor calibrating itself and establishing the level of corrosion within the network. So we've got about sort of 38 microns of corrosion in there. The red line is indicating when our units were brought online, and the green line at the end of that graph is indicating when we've moved the water into a non-corrosive state. So within about a week, we moved that water. So anything less than 20 microns is considered non-corrosive. We'd move that water into that non-corrosive state, and then we could start to clean up the system. So these are just some of the water quality levels testings that we took from that site in that process. So your top left-hand corner there is your dissolved and total ions. Your top right hand is your conductivity of the water. The bottom right hand graph is the chlorides in the network, and the bottom left is your pH. So in your top left hand corner there, you can see sort of the spike that you get in terms of the total dissolved ions and in the network, and that's to do with us agitating that debris we talked about, bringing that into suspension. And then the drop off in that is just carrying out that process, that resin rinsing, when we really had a go at breaking the conductivity of that water. So you saw the conductivity come right down. You saw the chloride levels come right down in the bottom right hand corner. And during that intensive rinsing process, that can push the pH levels down. But you can see that your magnesium anodes in your reaction tank will start to bring that back into balance, back to the right levels. The next case study is just a proof of concept that we did for a high street bank on their data centers, so a chill water network. And this proof of concept was sort of overseen by one of their own expert witness, and he wrote a 14-page report on the performance of our equipment on this site, and that's something that we can share with you if you did want a copy of that. But they basically had high bacteria counts, high TVCs. The client had an appetite for a more sustainable solution, so wanted to move away from chemicals. Again, they were faced with high chemical costs. And we had a 90-day trial on that site. So within that 90 days, we reduced their total viable counts, their TVCs, by 90%, their chlorides by 48.6%, the dissolved ions came down by 26.4%. And the client signed that project off within 45 days of that 90-day trial. And then they've rolled us out into the rest of their portfolio of buildings. Again, this was the third-party corrosion monitor on that site. So although they didn't have the same levels of corrosion, their issue was more bacteria. You can see within about 36 hours, we moved that water into a non-corrosive state, and then the cleanup process began. Just two more examples, just to show you different types of projects we worked on. So this was a typical communal and district heating scheme. So centralized boiler plant serving 215 apartments. Again, this site had serious water quality issues, which had led to the seals in the PIC valves in the HIUs on the site from being worn away, which meant none of your PIC valves were closing, giving you positive closure, which meant every apartment was bypassing water, which meant you were not getting any delta T across the main plant room. So people were getting charged huge amounts for the energy that they weren't really using. So we were installed again in the background. There was other companies involved in doing remedial work, in changing pipe work, and obviously changing component parts that have failed over quite a long period of time. And over 7 months, we brought that site back to VDI standards and back in line with what it needed to be. And finally, we've done some work with the NHS across the UK. And this project was with NHS Ulster, so the Northern Ireland Trust. They had a number of water quality issues since opening one of their new units, high counts across all areas of analysis. They were seeing component failures of PIC valves regularly. They were facing sort of expensive yearly costs in terms of dosing across, a number of different networks across a number of their sites. And still having problems and facing high chemical flushing remedial work costs. So they were looking for something different to see if we could help them out. So again, they installed our protective reaction tanks on a number of their different networks. We carried out a number of rinsing processes on some of those networks. And they saw a return on investment recovered within 10 months, and great results in terms of cleaning up their systems. I know when we started with them, in their words, they described the water quality initially as looking like Guinness. And they said by the time we'd finished, we'd moved it to looking like a weak lager shandy. So they'd seen a drop off in terms of, component failure and just an overall improvement in the water quality. And the work is ongoing there because on that site, the levels of conductivity were sort of over 7,000 microsiemens, and we're still working to break the back of that. But they've seen operational improvements, and have rolled us out across a number of their different networks now. So hopefully that just gives you a good overview of chemical-free water treatment. Your key takeaways is really, what we're doing is controlling those causal elements of corrosion within the water to stricter levels. So your dissolved oxygen, your pH, and your conductivity, and you get those things right, all the other levels fall into place. So yeah, that's the end. And yeah,